In the name of Almighty God, I am Master Sankoshi, and today I want to talk about inverse spillover and dimensionality effects on interstitial hydrogen. It was written by Commander Palson and others from the Department of Physics and Astronomy, Uppsala University. Nanoscaling interstitial metal hydrides offers opportunities for hydrogenation applications by enhancing kinetics, increasing surface area, and allowing for tunable properties. The introduction of interfaces impacts hydrogen absorption properties and distribution heterogeneously, making it, however, challenging to examine the multiple concurrent mechanisms, especially at the atomic level. Here we demonstrate the effect of proximity on interstitial hydrogen in ultra-thin single-crystalline vanadium films by comparing hydride formation in identically strained Fermit V and Chrome V superlattices, pressure, concentration, and excess resistivity. Isotherms show higher absolute solubility of hydrogen, higher critical temperature and concentration in the chrome V superlattice. Direct measurement of hydrogen site location and thermal vibrations show identical occupation of octahedral Z sites at room temperature with a vibrational amplitude of 0.20 and 0.25 over a wide range of hydrogen concentrations. Our findings are consistent with a more extended region of hydrogen depletion in the vicinity of the Fermit compared to chrome, which showcases an inverse of the hydrogen spillover effects, advancing the understanding of the interface effect resolves previously puzzling differences in the hydrogen loading of the Fermit V and Chrome V superlattices and is relevant for advancing both catalytic and storage. Hydrogen in metal can occupy in an interstitial sites, enabling high hydrogen storage capacity, yet simultaneously cause highly determinantal effects like hydrogen-induced embrittlement, exhibiting a high hydrogen mobility even at lower temperature. Interstitial hydrides have been used for purification, hydrogen sensing, and act as catalysts. Hydrogen absorption is strongly affected by composition and structure at the atomic scale, which provides opportunities to improve reaction kinetics and or reduce the enthalpy of formation to meet requirements for application. Particularly, interfaces influence metal hydride formation through a number of mechanisms which are challenging to disentangle. For example, a strain due to elastic boundary conditions at interfaces alters the local electronic structure at interstitial sites, leading to changes in local binding energies of H and elastic hydrogen-hydrogen interaction, which affects thermodynamic properties, which was described in references 6 and 7, site occupation in references 8 and 9, and thereby also diffusion. In the case of the magnetism, partial hydrogenation leads to the formation of localized dihydrogen magnesium clusters, where electronic structure change induce interface polarization, slowing hydrogen sorption kinetics and leaving surfaces partially hydrogen-free. In contrast, the solubility at surface and surface absorption side of the PD can be enhanced due to the weakened metal binding and surface strain from fewer neighboring atoms. Furthermore, missing hydrogen neighbors at surface of ultra thin films can decrease both the mean hydrogen-hydrogen interaction and critical temperatures via finite size effects, effect of the surrounding chemical environment on the hydrogen absorbing material, also called proximity effects, are therefore potential levers for tuning hydrogen uptake. Interface effects can be studied by sandwiching different materials in a superlattice with high crystal quality and identical strain states. Strain states are hydrogen-absorbing films with distinct adjacent non-absorbing materials can be tuned by the layer thickness ratio and substrate adhesion, and are known to influence thermodynamic properties. Hence, it is crucial to keep the initial strain state at the same when investigating proximity. The hydrogen absorbing material chosen in this study is vanadium, which is representative of a wide class of interstitial hydrides, absorb hydrogen into distinct interstitial sites and exhibits a rich thermodynamic phase diagram. In bulk, vanadium hydrogen occupies different interstitial sites above and below the critical temperatures. T sites alpha phases and O sites beta phases respectively, and exhibits regions of coexistence and suppressed spin nodal. The components neighboring V are either fermite or chrome, for the which hydrogen absorption is endothermic at the studied conditions. Previous attempts focusing on the reciprocal space techniques and density functional calculations observe variations in hydrogen-induced lattice expansion and thermodynamic properties, which were attributed to site occupancy differences. Therefore, through careful reanalysis in this work will reveal an underlying effect whose origin can be traced to the extension of hydrogen-depleted layers at the interface, explaining the observed differences in expansion coefficients without change in site occupation. Consequently, an intrinsic finite size effect is induced in the central layer due to a lowering of the effective thickness of the vanadium layer, while hydrogen spillover effects at the interface to which is related to references 22, 23, 24. The migration from one active site to another have been shown to enhance hydrogen storage in a variety of materials. Our findings suggest a contrasting phenomena, specifically the absence of hydrogen near an interface with a non-absorbing metal influenced by the type of the adjacent element corresponds to an inverse of hydrogen spillover. To investigate these effects, we employed the direct real space methods for determining hydrogen concentration. Site location and vibrational motion using energy resolve and channeling nuclear reaction analysis NRA with Ni ions. Phase boundaries were extracted via pressure composition and resistivity isotherms using calibrated optical transmission as a proxy for hydrogen concentration. The original of the optical response, open hydrogenation of fermite chrome V superlattices was investigated in 2028, 29, 30, and demonstrated to be dominated by lattice expansion. A thermodynamic analysis of confined hydride thin films in superlattices. The inset in Figure 1 illustrates the Fermit V and Chrome V superlattice samples with a thickness ratio of 2 per 14 monolayers on oxide magnesium substrates and covered with 7 nanometer of PD to catalyze the dissociation of the molecular hydrogen and to protect the sample from oxidation. Both superlattices have a crystal coherently compared to the thickness of the films and are under the close to similar tensile and compressive biaxial strain the plane which the interlayer roughness of the positive negative one monolayer. The absorption of hydrogen is fully reversible and results in one-dimensional out-of-plane volume expansion, while the samples remain metallic. The pressure concentration isotherm reciprocity for Fermi V and Chrome V in Figure 1, Section R revealed that the magnitude of the hydrogen uptake at equal pressures scale significantly differently for the two samples. V in proximity to Chrome absorbs approximately 1.5 times as much hydrogen compared to the Fermite and is much closer to the bulk solubility. Both exhibit onset of the pressure plateaus, which is clear temperature dependence, while the plateaus slopes and the equilibrium pressures are lower for chrome V than fermite V at the same temperature. In equilibrium, hydrogen pressure can be related to the chemical potential of the metal hydrogen system from which thermodynamic properties can be determined. In the center of the plate region, the derivative of the chemical potential approaches zero as the temperature is lower, indicating the onset of a critical point in the region. 0.05 H per V and 0.15 H per V for the two samples. So you see there is a figure one. Figure one illustrates thermodynamic analysis of the vanadium hydride films embedded in the superlattices. There are this section that you see that we have a hydrogen pressure as a millibar. You see that we have a Fermi to Pervi, and the blue lines is about 200 degrees of Celsius, and green lines is about to 160 degrees of Celsius, and the next one, red and yellow, are in chrome and V superlattices. Red is 200 degrees of Celsius, and the yellow line is 160 degrees of Celsius. You see that they have a less when there is near to the chrome, we have a less pressure for hydrogen based on the millibar. And here in the next section, the concentration in the axis, x-axis, and also in the y-axis, we have a delta rho, which is and it's a portion of the delta rho per delta rho zero, which is talking about the density and concentration. You see that we have based on this legend, for example, blue and green are related to the fermite, and red and yellow are related to the chrome. And you see that the green and blue are have a more density on concentration, but near to the chrome we have no such intensity in the concentration. Section of pressure composition is the term of the fermite V and chrome V superlattices at 200 degrees and 160 degrees. Hydrogen concentration refers to the average hydrogen concentration in vanadium fields extracted from calibrated optical transmission at 625 nanometer. Section B is the terms of change in excess resistivity delta rho normalized by rho zero without hydrogen, and C delta P per rho zero enhanced for UHV to low pressure region, highlighting an initial decrease for a Fermite V. Section T shows the delta rho per rho zero of the chrome at the different temperatures: 225 degrees of Celsius, 200 degrees of Celsius, 160 degrees of Celsius, subtracted by a linear function which is slope at ranging between 0.878 till 0.863 to enhance discontinuity from temperature independent behavior. The dashed lines mark the discontinuity edges at 160 degrees of Celsius. Phase boundaries are quantitatively explored, analyzing relative change in the resistivity, rho or density that result from scattering of the electrons by perturbations in the average potential landscape, and are sensitive to change of the hydrogen ordering in metals. Figure 1b shows its terms of excessive resistivity quantified by rho and rho zero per rho zero is equal to delta rho per rho zero, where rho zero is resistivity of the As ground sample at temperature T, the delta rho per rho 0 Ct is a term of both superlattices are of similar shape, but resistivity change in the Coulomb V extend further in average hydrogen concentration similar to rho Ct is a term in figure 1a, a minor initial decrease of delta rho in Fermi V for a very low hydrogen pressures visualized in figure 1. C indicates enhancement of crystal quality. This finding implies the presence of a low concentration of defects in the vanadium, such as the vacancies occupied prior to the interstitial sites, which cause a small concentration offset 2.5% till 3.5% in the calibration, as suggested in the reference 30, with increasing hydrogen contents. The delta rho per the rho 0 Ct terms are closely independent of temperature. However, within a small region around zero point 0.1 H per V and 0 in chrome V, sudden drops in the density appear below the 200 degrees of Celsius, which is demonstrated in figure 1d, enhanced by subtraction of linear function from the data to analyze intrinsic changes in the electrical properties of the tin metal hydride films. Delta rho per rho 0 C has previously been expressed as a combination of several contributions. We separate the different features of delta rho per rho 0 and correlate them to appropriate of the metal hydrides as follows. Bulk-like metal hydrides are known to exhibit a parabolic behavior in delta rho rho 0 for continuous phase transition in the absence of phase separation, which we attribute to the term rho hc. The effect originates from conduction electron scattering from change to the average potential. This scattering increases until the interstitial sites are half occupied. Beyond this point, the electrons scatter from the potential variations caused by the remaining unfilled and field sites. This behavior is seen in, for example, the alpha to alpha purine transition in bulk VH in figure 1b and 2d. Such a parabolic behavior is observed centered around the zero point 0.1 H per V, while superimposed by a second monotonically increasing contribution of a large increase in Fermi V versus Chrome V. The effect has been observed in thin films and superlattices and is suspected to originate due to the presence of interfaces and hydrogen depleted layers, and identified as second contributions a row layer. The deviations from the temperature independent behavior, the sudden decreases in delta rho per rho 0 around zero point 0.1 HV highlighted in the figure 1d for chrome V, are associated with changes in row arch C. As variations in the ordering of the lattice constituents influence the electronic scattering, the sudden change in the slope with decreasing temperature indicated prompt change in concentration fluctuations. Similarly, sharp resistivity minima in rho HC below the critical temperature are observed for the TAH system. The hydrogen concentrations and temperatures corresponding to the discontinuity edges in rho Hc extracted by comparing delta rho per rho 0 curves at various temperatures and identifying sudden changes in the slope are shown in figure 2. Solid circles. The concentration change into the nearest measurement yields a measure for uncertainty. We identify a phase boundary and approximate a parabolic shape, yielding a lower critical temperature and critical concentration in Fermi V, namely it is 0.078 HV at it is nearly 160 degrees of Celsius versus 0.133 HV at which is really near to the 196 degrees of Celsius in Coulomb V. The onset in the Coulomb V can already be observed at 200 degrees of Celsius in Figure 1D. The lower critical temperature in FAE or Fermi V is also reflected in rho CT pressure plate of a lower incline than Chrome V at the same temperature. Plates are expected to be flat below the critical temperature due to equilibrium conditions between different phases. Sloped plates indicate a variation in stress distribution in the V layers. So you see the bell shape in the figure 2 proximity effect on the phase transition of the vanadium hydride. In the x-axis we have a concentration which is based on the H per V, and in the y-axis we have a temperature based on the degrees of Celsius, and it starts from the 0 until the 240 degrees of Celsius. Solid circles phase, and we have a different section A, B, C, D, and you see that in the blue circle we have Fermi V superlattice, and the red circle we have a chrome V superlattice here. Solid circles phase boundaries for chrome V and Fermi V superlattices obtained from the sudden change in the slope of the delta rho per rho 0 is a term as indicated in the figure 1D. Dotted lines follow a fitted parabolic function as a guide to the eye. Mark hydrogen concentrations in the chrome V A until D and the Fermi V D until V, where site location analysis is performed by channeling NNRA, presented in Figure 3, uh, the sections from the all until to the F. Inset illustration demonstration hydrogen depleted layers of different thicknesses layering the effect thickness of the vanadium layer, which reduces film size effect on the phase boundaries. A decreasing ordering temperature has been associated with the decreasing layer thickness arising from the missing neighbors at the interfaces, similar to finite size effects in the magnetic layers and non-sized ice crystals, while the thickness of the vanadium films is identical for the Fermi V and chrome V. The thickness of the hydrogen-containing vanadium layer may not necessarily be the same if proximity to the fermite induces a large hydrogen depleted region compared to the chrome, as illustrated in the inset of the figure 2. The nominal hydrogen concentration normalized to the atomic fraction of the V atoms in the superlattices is averaged over the absorbing and non-absorbing V layers. A variation in the amount of non-absorbing V for a fixed number of the hydrogen atoms in absorbing V results in the different average hydrogen concentration. Thus, the significant differences in average hydrogen uptake and critical concentrations support the proximity effect on the extent of the depletion layer. Hydrogen-depleted V-layers have been reported at the interface to vacuuming and to Fermi. Extensions of the two between the 4 until 5 have been visualized by the atom probe tomography and deduced from the NRR experiments. Two between 2 and 3 monolayer infrared from the critical temperatures in the and one with the lowest SI unit determined with the neutron reflectometry. Findings by W. Hung and his colleagues in the reference 21 indicate a larger estimated depletion of the 2.25 in the ferrite V as compared to the 1.6 as a monolayer in chrome V. Another observation from the rho CT and delta rho per rho 0 CT is terms in figure 1 is the reversible hydrogen AB and desorption without the occurrence of hysteresis. Hysteresis is linked to coherence elastically deriving phase transformations and interstitial size change. The size preference depends on the initial lattice strain and hydrogen-induced increase in strain, which scales differently depending on the type of the site occupation. On top of plane Lattice expansion coefficients of clamped vanadium were found to be 37% to 50% larger for oxygen than for TZ occupation due to the anisotropy of the local strain field. The concentration at which a site change occurs depends on whether hydrogen is AB or absorb, causing hysteresis in isotherm measurements. The absence of hysteresis in the vicinity of the phase boundaries does suggest transition without a change in hydrogen site occupancy. However, with increasing initial biaxial compressive strain of vanadium, the hysteresis gap is expected to decrease and can therefore be very small in the fully strained superlattices. Further insights into site occupation can be gained considering that the optical response used to determine the hydrogen concentration for isotherm in Figure 1 correlates with hydrogen-induced volume change. The isotherm obtained for the T is less than Tc and T is greater than Tc exhibit excellent overlap for delta rho per rho 0 and consistent change in the rho Ct isotherm over the whole temperature range. These findings and the absence of the hysteresis suggest that the observed phase transition occurred without a change in soil occupancy, in stark contrast to behavior of the hydrogen in the bulk vanadium. These results indicates that the control over boundary effects can influence site occupancy and thereby inhibit deleterious changes such as embrittlement due to the side chains and large differences in specific volumes of the hydrous phases. Now I want to go through the real space lattice location to test this hypothesis. Site locations of interstitial hydrogen were directly investigated via N and 2 NRR at room temperature for different concentration indicates as these lattice in figure 2 for chrome and also Fermi. These whole experiments were conducted for average concentrations well above the phase boundaries, while C and F were performed within the parabolic phase boundary. The cross-sectional distribution of hydrogen atoms in superlattices was found to be homogeneous within the depth resolution of several nanometers. However, at the lowest concentrations, variations in the distribution were observed, as demonstrated in reference 30. Site occupation is probed exclusively in in the center of the hydrogenated Fermi V superstructures and is derived from the resonant nuclear reaction yield with hydrogen in channeling geometries, which directly correlates to the nuclear counter probability of N ions to hydrogen interstitials. Figure 3 shows the normalized channeling Y yields for the angular result scans over the 110 and 310 and 110 planes of the superlattice crystal. The observed channeling dips in the Y yield relates to the shadowing of hydrogen atoms by lattice atoms and demonstrate oxygen occupancy open comparison to the simulations of various soil positions. In reference 26 calculated NEPs of channeling anions to hydrogen and oxygen sites of different thermal vibrational amplitudes are plotted as solid lines. The corresponding residuals of the simulations of the experimental values shown in blue in figure 3 can be used to judge the best fit in the quorum and also Fermi site occupation is identical of the oxygen type with thermal vibration amplitudes of 0.20 and 0.25. The observation of identical hydrogen vibrational amplitudes in both superlattices indicates similar vibrational characteristics and elastic properties of the metal hydrides within the measurements uncertainty. These thermal Vibrations correspond to the zero-point motion of hydrogen in the potential wave of the interstitial site, which is seemingly independent of the adjacent metal within the hydrogenated layer of the and the hydrogen concentration above the phase transition. Within the phase boundary, the yields dips are less pronounced, more so in Fermite than in the chrome, and the oxygen occupation with the 0.25 vibrational amplitude cannot reproduce the experiment with a 3 sigma interval. The difference in the observed channeling pattern can result from occupation of both T and oxygen sites, the larger vibrational amplitude or small displacements decreasing the shadow of the hydrogen atoms, or partial occupation of the less shadowed or randomly distributed defect sites. For Fermi experiments, defect sites could account for a significant part of the hydrogen inventory, while the exact distribution of the effect sites in the superlattice is known. Although the different configurations are in principle distinguishable by evaluating multiple geometries due to the large uncertainty to the normalized while the quantitative analysis doesn't yield ambiguous results. The large uncertainty in Y yield at a low concentrations stems from a low signal to background ratio when employing ion beam currents to avoid beam-induced hydrogen loss. Consequently, the determination of the exact site locations from the data acquired in experiments C and D and also below the critical concentration remains elusive under these conditions. The observed site occupancy aligns with the theoretically predicted influence of axial compressive strain. In reference 8, revealing the preference of the oxygen sites for the lattice strain above the chrome A is greater than 1.04, which is reached at about zero point 0.2 hydrogen V in Fermi's initial strain to the C per I is equal to 1.01. In confined thin films, oxygen occupation doesn't necessarily imply on the order beta phase as in bulk vanadium, and a phase transition upon increasing the temperature beyond the critical temperature must not implicate a change in soil occupancy as suggested by the isotherm measurement in figure 1. Now I want to go through the proximity effects influence hydrogen distribution. We have studied hydrogen absorption in single crystal in several lattices featuring stacks of the ultra-thin Bandio films in the proximity of fermitochrome. Despite their identical structure and strain state, the average solubility of the hydrogen is large in bandium in proximity to chrome, and phase boundaries are shifted such that the critical temperature and concentration are higher compared to vanadium layers in proximity to ferrite. Furthermore, real space soil location below the transition temperature level reveals identical site occupation of high oxygen type with consistent thermal vibrational amplitude indicating difference between the average zero-point energies. Optical transmission and excess resistivity measurements indicate that the site preference is temperature independent with the range of the 100 to 225 degrees of Celsius. So you can see the three sections for the figure 3. The first one is related to the relative sample orientation, and also let's talk about the sigma exponentially normalize one channeling yield resulting from the angular result NNRR for detection of the hydrogen location in chrome and also fermite. Loaded to different concentrations made in the figure 2, the angular line scan crosses several crystal planes 100, 300 pin and also 110. close to the 0.1 axis of the superlattice's hydrogen is probed exclusively in the center of the superlattices, corresponding to the anyons energies of the 6.57 megaelectron volt and 6.55 megaelectron volts respectively. The solid lines represent the simulations of the NEP to hydrogen oxygen interstitial sites of various thermal vibrational amplitude. The lower plots show that the corresponding residual normalized by the standard deviation sigma, and in setting the E illustrates projection of the vanadium yellow sections unit cell along the 001 for hydrogen in the red sections, and also T sites. These findings provide strong evidence of a larger hydrogen-depleted layer at the interface to fermite than to chrome, confirming earlier conjectures, which indirectly yields a thinner absorbing layer, which in turn is subject to finite size-induced layering of the critical temperature. Previous experimental studies on hydrogenated fermite chrome found enthalpy differences via optical transmission measurements. Furthermore, deviating volume expansion above the phase transition temperatures of deuterated samples was observed via neutron reflectometry. These findings can all be reconciled by the presence of the differently sized depletion layer at the interface in V, an effect that displays an inverse of hydrogen spillover. The origin of the depleted layers has been discussed in the literature as alloying of the V with the fermite chrome decreases hydrogen solubility. Chemical intermixing at the interface contributes to hydrogen depletion at the interface, while both fermite and chrome have low negative enthalpies of mixing with V negative 7 and negative 2 megaelectron volts per atom. Chrome has slightly less negative enthalpy of mixing, thereby providing a lower driving force toward intermixing. Nevertheless, hydrogen-depleted regions in pure vanadium were separated from the intermixed fermite by Gemma and his colleagues in reference 38, and were also observed near the vanadium surface to vacuum by E. Bilter and his colleagues in reference 37. Modulated rigidity is considered in 46 as hydrogen distribution is governed by the energy cost of accompanying volume expansion, calculated to have a screening length of 2 to 3 monolayer. However, the shear modulus of chrome, which is equal to 115 gigapascal, is higher than the fermite, which is 82 gigapascal. So, implying the opposite effect observed in this work. Earlier studies suggested electrostatic repulsion of hydrogen due to charge transfer introducing interface dipoles, while electrostatic effects are conceivable as fermite has two additional conduction electrons when compared to chrome, as a theoretical study in 46 finds them mostly screened as electrons contribute to a common electron gas. Calculated densities of states presented in 19 demonstrate distinct impacts on VP negative 5 and the D bands at the interface with chrome fermi, characterized by a small charge transfer from the first atomic V layer to chrome 0.2 electron and twice as large to the fermite 0.4 electron. The chemical binding of the hydrogen around -7 electron volt was found unchanged both at the interface and in the center of the film, while the direct correlation to the electronic influences is not evident. From these considerations, our findings suggest that their potential role in the observed proximity effects on the hydrogen-depleted layer. Additionally, spin polarization resulting from the magnetic effect is conceivable, given that the fermite is ferromagnetic and chrome antiferromagnetic. These, however, are to date unexplored. The inverse spillover effect discussed here has a large bearing on the fundamental understanding of the important spillover effect seen in the other systems, and a careful systematic approach at the atomic level holds considerable promise for elucidating its underlying mechanism. Once fully understood, spillover effects can be leveraged to tailor thermodynamic, kinetics, and catalytic properties of metal hydrides, enhancing their performance in various applications. Now I want to go through the experimental method. Superlattice samples, the Fermit V and Chrome V superlattice are epitaxially ground on polished single crystalline oxide magnesium 001 via DC magnetron sputtering. The Fermit Chrome V layers have a nominal thickness ratio of 2 per 14 monolayers, which minimizes the elastic energy in the bilayer, and repeated 20 and 23 times, respectively. Elemental composition analysis employing Rutherford backscattering spectrometry (RBS) with helium-2 mega-electron volumes reveals slightly higher Fermit and Chrome concentrations with a true ratio of about 1 per 6. Isotherm measurements, pressure and resistivity isotherms, were simultaneously measured by optical transmission at 625 nanometer at 4 probe resistance measurements row density between 100 degrees of Celsius to 225 degrees of Celsius in a UHV chamber, described in detail in 27 reference. Relative changes in the optical transmission are derived via the Lambert-Beer law as a minus ln I per I0, and excess resistivity is quantified by rho 0 per rho 0 is equal to delta rho per rho 0, where I0 and rho 0 are measurement at UHV conditions. Changes in the optical transmission due to phase transition in the capping layer PD are not expected at these pressures and temperatures 50, which is related to the references 51 and 52. The hydrogen pressure and P is increased stepwise, and data is extracted after thermodynamic equilibrium is reached. The calibration of the log ln I per I0 to absolute hydrogen down by the N and NRE are in the references 28 and 29 and also 30 is of linear correlation, however, with small axis offsets in opposite directions for the two superlattice systems. The negative offset for the Coron V has been attributed to a systematic uncertainty arising from a minor drift in optical intensity over prolonged measurement periods and can be omitted in the analysis. The positive offset in the Fermi V is attributed to hydrogen first occupying defect sites, the presence of which is revealed by the resistivity measurements shown below in Figure 1C of this board. As the occupation of these lattice defects is not observed to induce a response in negative ln I per I0, only the slopes of the calibration curves are used to calibrate the optical transmission at 625 nanometer minus ln I per I0 converts average hydrogen concentration in vanadium CH per V via 1.20 positive negative 0.06 and 1.06 positive negative 0.03 for chrome V and also fermit V respectively. Direct detection of hydrogen concentration and site location, then to investigate hydrogen distribution, site location and vibrational motion in the superlattices at different hydrogen concentrations. The samples were further prepared for excision ion beam analysis. A thin layer of trioxide dialuminum was deposited by reactive magnetron sputtering, which slows hydrogen AB and desorption during the loading procedure and minimizing hydrogen desorption under UV beam exposure. The coated superlattices were loaded with hydrogen, thereby heated to 140 degrees Celsius and exposed to pressures up to 1 bar of the hydrogen gas. After several hours, the chamber was gradually evacuated and cooled to room temperature, and samples were subsequently transferred for ion beam analysis. For more details on the procedure, we refer to the 29 reference and also 54. Ion beam experiments using RBS and NRO were performed at the 2 MeV and 15 SDH2 tandem accelerator, Uppsala University, Sweden, employing a anion beam between an energy range of the 6.37 and 6.7 megaelectron volt with fluences below 2 nano A. Backscattered anions are captured by a solid-state detector at a scattering angle of the phase equal to 160 degrees. The gamma, which is equal to 1.43 megaelectron volt radiation resulting from the H and alpha gamma C nuclear reaction. The energy is equal to 6.385 megaelectron volt megaelectron volt is detected with a bismuth germanate scintillation crystal placed outside the experimental chamber behind the sample. Accurate hydrogen concentrations are extracted from NRO excitation profiles, positioning the resonance energy at varying deep depths in the target for non-channeling geometries. As the depth resolution and several nanometer hydrogen distribution is averaged over several bilayers of the superlattice. The current normalized gamma yield is calibrated to H implanted SI standard of the 18.5%, considering change in electronic energy loose cross-section of the metal hydride compound according to the analysis procedure described in the reference 56. The location of interstitial hydrogen in the unit cell is determined by performing simultaneous channeling NNRO and NNRBS measurements and Monte Carlo simulations evaluating multiple crystal planes in a single angular resolve scan. The analysis of channeling NRBS through the superlattices, which is presented in reference 30, gives a quantitative measure of ion trajectories by fitting ion flux distributions as simulated with the Monte Carlo method-based program. Flux 7. Thereby, a normalized average nuclear counter probability (NEP) of a ion projectiles to lattice atoms drive, which is evaluated against normalized experimental RBS channeling yields. The supporting program YIMP7 calculates the NEP or a nuclear encounter probability of the anion flux with thermally vibrating interstitial hydrogen occupying certain interstitial sites employed to analyzing channeling and NRR. Thank you so much for watching my tutorial video until the end. If there is any simulation for this article and literature, you can download it from github.com/masterscript or the github.com/script or github.com/safroscript. Today is 21st of June 2026. Time is 3:40 p.m.